In this lecture, we will discuss some fundamental continuous time signals. From our previous lectures, we already know that a continuous signal has no discontinuity from its starting point to its end point, and it can take any value within a given interval, such as between 1 and 2. A signal can also exist close to zero and can even have negative values. For simplicity, in this lecture, we will focus on fundamental continuous time signals for positive values of time, that is, for time greater than zero. Continuous time signals, which are also called analog signals, are generally denoted by x of t. However, depending on the type and nature of the signal, we can use other symbols as well. Let us start with the most basic continuous time signal, the unit impulse signal. The unit impulse signal is one of the most commonly used and important signals in signal processing. Mathematically, it is denoted by delta of t and is defined as follows: delta of t equals 1 when t is equal to 0, and 0 when t is not equal to 0. This means that the impulse signal exists only at a single point in time. When t equals 0 and has 0 magnitude everywhere else, whether t is positive or negative, the shape of this signal is very simple. According to its definition, when time is equal to 0, the signal has an amplitude of 1, and when time is less than 0 or greater than 0, its magnitude is 0. For example, if we represent the signal from -5 to +5, it will only have a value at t equal to 0 and will be 0 everywhere else. Ideally, the signal exists only for an instant in time, meaning it has no duration. The unit impulse signal is a very important concept because it forms the basis for many other signals and is used in analyzing and testing systems in signal processing. Since this is a continuous time signal, it has no breaks or discontinuities. Now, let us discuss time shifting of the impulse signal. We know that the impulse normally exists at t equal to 0, but we can shift it along the time axis. This means that the signal can be delayed or advanced. A time delay shifts the signal toward the right, positive time axis, while a time advance shifts it toward the left, negative time axis. For example, if we delay the impulse signal by 2 units, it means the impulse now occurs at t equal to +2. The equation of this delayed signal is written as delta of t minus 2. The minus sign here represents delay. On the other hand, if we advance the signal by 2 units, meaning it occurs earlier in time, the equation becomes delta of t plus 2. The plus sign indicates advancement. So remember that a minus sign inside the parentheses represents delay, while a plus sign represents advancement. These two types of shifting, delay and advance, are very important because they help us represent when a signal occurs in time. Whether we delay or advance it, the basic shape of the signal remains the same, only its position on the time axis changes. Now, let us move on to the next important signal, the unit step signal. The unit step signal is denoted by u of t. It is defined as a function that has a magnitude of 1 for all values of time greater than or equal to 0 and a magnitude of 0 for all values of time less than 0. Mathematically, u of t equals 1 when t is greater than or equal to 0 and 0 when t is less than 0. This means that the signal starts with a value of 0 for all negative time, then suddenly jumps to 1 at t equals 0, and remains at 1 for all positive time. The point where the signal jumps from 0 to 1 is called the step point, which is why it is called a unit step signal. If we plot this signal, we can see that when time reaches close to 0, its value becomes 1, and for any value of time greater than 0, it stays constant at 1. As time becomes less than 0, its value remains 0. In simple terms, the unit step signal is 0 before t equals 0 and 1 after t equals 0. If we compare the unit step signal with the unit impulse signal, we can clearly see the difference. The impulse signal has a value of 1 only at t equals 0 and 0 everywhere else, while the unit step signal has a value of 1 at t equals 0 and continues to stay at 1 for all future times. The unit step signal is also used very frequently in signal processing and system analysis because it helps us understand how systems respond to sudden changes or steps in input. So, in summary, we have discussed two important continuous time signals so far: the unit impulse signal and the unit step signal. The impulse signal exists only for a single instant in time, while the step signal starts at t equals 0 and remains constant afterward. Both signals are fundamental in understanding more complex signal behaviors in future lectures. In the previous lecture, we discussed the unit impulse signal. We learned that the impulse signal has a value of 1 only when time is equal to 0, while the unit step signal takes the value of 1 at time equal to 0 and remains 1 for all values of time up to infinity. This is the key difference between the impulse and step signals. Now we can also shift the unit step signal in time. First, let us consider shifting the step signal toward the right, which means delaying it. In this case, the signal starts at a value greater than 0, for example, at time equal to 2. This happens because we have shifted the signal 2 units toward the right side, which represents a time delay. According to the concept we studied earlier, we can represent this delayed signal mathematically as u of t minus 2. The minus sign in the equation indicates that the signal has been delayed. Similarly, we can also advance the step signal in time. When we advance a signal, we move it toward the left side of the time axis, that is, toward the negative direction. For instance, if we advance the signal by 2 units, it will start at time equal to minus 2. The equation for this signal is written as u of t plus 2. The plus sign here represents advancement. So remember, the minus sign represents delay, while the plus sign represents advancement. By shifting the signal, we can control when it starts in time without changing its shape. Both the impulse signal and the unit step signal are among the most commonly used signals in signal processing. They are fundamental to understanding how more complex systems behave. Now, let us move to another important continuous time signal called the unit ramp signal. The ramp signal increases linearly with time, which means it has a constant slope. Mathematically, it is defined as r of t equals t for t greater than or equal to 0 and 0 for t less than 0. In other words, the signal takes the same value as the time itself for all positive values of time. For example, when time is 0, the signal is 0. When time is 1, the signal is 1. When time is 2, the signal is 2, and so on. This signal does not exist for negative time values. If we observe the ramp signal, we can see that it starts from 0 and increases linearly with time. It has a constant slope, which means it grows at a steady rate. When time equals 1, the signal's amplitude is 1. When time equals 2, the amplitude is 2. And when time equals 4, the amplitude is 4. The magnitude of the signal is equal to the value of time, and that is why we say the ramp signal increases uniformly. This is the simplest form of a continuously increasing signal. Next, let us discuss another very important signal called the sinusoidal signal. A sinusoidal signal is a periodic signal that oscillates above and below the time axis in a smooth and repetitive manner. It is mathematically represented as x of t equals a times sine of 2p ft, where a is the amplitude and f is the frequency. The amplitude represents the peak value of the signal, while the frequency is the number of cycles the signal completes in 1 second. The frequency is the reciprocal of the time period. When we plot a sinusoidal signal, we can see that it repeats itself after equal intervals of time. For example, if the amplitude A is 5, the signal reaches a maximum positive value of +5 and a minimum negative value of -5. The signal starts from 0, rises to its positive peak, then falls to its negative peak, and returns to 0 to complete one full cycle. This pattern repeats continuously over time. Suppose the time period of the signal is 2 seconds. This means that in every 2 seconds, the signal completes one cycle. Therefore, in 10 seconds, the signal completes 5 full cycles. The amplitude, frequency, and time period are the 3 most important parameters of a sinusoidal signal, and whenever we need to generate or analyze such a signal, we must specify these parameters. Now, let us move on to the unit exponential signal, which is another essential continuous time signal used in signal processing. The exponential signal is defined as a function that starts with a maximum amplitude and then gradually decreases over time. It is mathematically written as e to the power of minus a t, where a is a positive constant. The exponential signal exists only for time greater than or equal to 0 and has an amplitude of 1 at time equal to 0. When we observe the shape of the exponential signal, we can see that at time equal to 0, the amplitude is 1, which is its maximum value. As time increases, the amplitude decreases exponentially and approaches 0. For example, when time is 1, the amplitude is e to the power of -1. When time is 2, it is e to the power of -2, and so on. The value keeps decreasing but never becomes exactly 0. The exponential signal is very important in signal processing because it models many real-world systems where signals decay over time, such as electrical discharges, sound fading, and other natural phenomena. The key property of the exponential signal is that it starts with its maximum amplitude and then gradually loses its energy as time increases. To summarize, in this lecture we studied several fundamental continuous time signals. We began with the unit impulse signal, then explored the time-shifted versions of the impulse and step signals. After that, we discussed the unit step signal and how it can be delayed or advanced in time. We also studied the unit ramp signal, which increases linearly with time, and the sinusoidal signal, which repeats periodically with a specific amplitude and frequency. Finally, we examined the unit exponential signal, which starts with a maximum amplitude and decays over time. These signals form the foundation for understanding more advanced concepts in signal processing, and we will use them frequently in the upcoming lectures.